taking the capstones.
Okay, welcome everybody to the second Visualization and Data Science lecture. Last time I didn't really finish my slides, so I'll be going over some of the things again, and we'll be talking a little bit about the administration, what it will take for you to do well in this class, and then I'll move over to perception. So we'll be talking about how does our visual system work, what are the caveats that we have to take care of, and I've also prepared an exercise. So I'm guessing that we probably won't be finishing up with perception and that we will do that again next Thursday. And from now on, we'll be always doing Tuesdays for the next couple of weeks will be a technical lecture. And then Thursdays is going to be like a theory lecture. This is going to happen for at least 6 or 7 weeks now. And so if you, for example, are really proficient in HTML and CSS and SVG, next Tuesday is not going to be very exciting for you. But I also still want to cover it because I don't want to lose anybody. And then the week afterwards we'll talk about JavaScript, about ES6, what you can all do with JavaScript. And then we'll be starting to talk about working with D3 in terms of technical content. Okay, so here are my stated course goals. Like I want to teach you, and you should be learning how to efficiently visualize how you can apply fundamental principles and techniques, how you can design visual data analysis solutions, and design both from talking to people to understand their problems and their goals, to coming up with sketches, to refining those sketches, to realizing this in a prototype, and then finally also to implement them as interactive data visualization. And so as a side effect, you'll be acquiring some web development skill in this class, and we'll be teaching some web development. As I already mentioned, we have these different course components. The lectures introduce theory, and the design critiques, like what I've prepared here, are really here for you to develop an eye for design, to really think critically about visualizations, because before you can actually do a good create a good visualization yourself, you have to know what makes the visualization good and bad. Then we'll have the labs, which will be Wednesdays. So we will have one lab next Wednesday. This lab will introduce the homework 1, which will be like a very simple SVG plots manually created. So Carolina will go through the homework and she will then give you an exercise which is similar to the homework that you can do while you're there and ask questions. Again, this is going to be pretty simple, so if you're like a CS major in your 4th year, then this might not be that exciting for you. Then of course we have the homeworks. As I already mentioned, there's going to be 6 homeworks, 4 easy and short ones for a week. Really easy at the beginning, but continuously getting more difficult. And the 5th and the 6th homework will be you creating multiple coordinated view visualization projects that will be a lot more intricate. You'll be creating maps, you'll use interactivity, and those will be 2-week homeworks, and they will be weighted higher, and you'll need a lot more time to complete them. And then your final project gives you a chance to go through a complete visualization project. I'll be talking more about the project at some future time, but essentially it's a team project. You should team up with 2 to 3 people, then you find your own data set, you develop a visualization design proposal, that you hand that in to us, we give you feedback, you develop a milestone that is functional in some way, you hand that in, we give you feedback, and then you develop the final version of the project. And the project is pretty important in terms of grades, because it's for 40% of your grades. I also mentioned this already quite a bit, so you will develop your design skills, your coding skills, and you'll learn about the visualization theory. And so we have these design studios, what I call these critiques, and you will be also asked to redesign something today, and we might have a lecture on design. For coding skills, there's the labs, there's the technical lectures that I'll be teaching, there's the reading, and of course, as always, when you program, you need to do it yourself. And you need to fail and make it better in Lookup and Stack Overflow, and so on. And then, of course, we'll be starting office hours next week, where you can go and ask questions. And the theory will be conveyed in lectures, like I'm doing it right now, and in the readings, as you can see, like we have a lot of recommended readings, and we also have a mandatory textbook. I would really recommend the textbook, especially for people like to follow that closely and to read it closely, who have like a deeper interest, because it's very well written. It's very dense, but it's well written and it's very comprehensive. Okay. If you're on, there is a YouTube channel, as I already mentioned, where we all will collect all of the videos that are being recorded here. This is also streamed live, and so you can revisit any of those lectures. And in terms of content, we will have like 3 different, essentially sections, whereas the first 2 here are a little bit interwoven. So we have technical foundations, where we'll talk about from everything from HTML to V3. The visualization fundamentals, like we'll do today, perception and other similar things. And then we have abstract data visualization, things like how do you visualize a table, how do I visualize graphs, how do I visualize maps, how do I deal with interaction techniques, and so on. So these are kind of the main components. There will be additional lectures that don't really fit that well in any of these 3 parts. You've probably seen the website by now. Please do take a look at the syllabus and read it. And I think mentioned this before, there is a companion course. So up till last year, I taught both abstract data visualization, things like maps, graphs and text and so on, and scientific data visualization in this one course, which was just like a very, very dense program for especially the scientific visualization. And so then we decided that we have 7 faculty who all do research in visualization. We have a lot of people who are in the graphics and visualization track, for example, and therefore we want to kind of give a deeper introduction into both topics and separated them out. So there is the visualization for scientific data taught by Chris Johnson, which will be first offered in the spring. And so there you will learn things like how do I visualize an MRI image, how do I visualize tensors in a spatial field, how do I visualize flow data, how do I visualize large-scale simulation data, for example, like combustion engines and so on, these kinds of things. The Slack channel for the public channels for all of these general questions. Obviously, don't post solutions for code, but feel free to ask questions. And therefore then, both the TAs and I and your fellow students can help you out. Use email for personal inquiries, so like permission codes, or I'm sick for whatever, like for this exam, or anything like that, where you have something personal to discuss, please email me directly. Please don't use Slack for that, because my email, I keep better track of my email than of Slack. For submissions, for the homeworks, we'll be using the Canvas system. We won't be using Canvas for much else, so we'll have Slack for communications, and we have the website for announcements and so on. The Canvas is mainly used for homework submissions and for grades. The projects will be submitted by simply posting your GitHub repository and tagging your release, so we won't be submitting projects via Canvas. My office hours are Wednesdays at 2 p.m. My office is in this building, 3rd floor, 3887. So feel free to come if you have questions about anything, be it technical, be it theoretical, be it of a personal nature. Please go ahead and see me. So these are the 2 required textbooks. Both of them are actually available to read on your computer for free on campus, provided by the library. This is the interactive data visualization. This is the old picture. Was just published a version 2, like a 2nd edition, just in end of August. And that 2nd edition is important because it covers D3 version 4, which we will be using compared to this book that covered D3 version 3. So there are some subtle differences between those two, and so if you look at the second edition, you never have to worry about version 3. And this is an academic textbook that really covers mostly information visualization in depth, and you will see that many of my slides are structured around this book. In terms of programming, I mentioned this before, we will be developing everything in JavaScript. We'll be using the latest version of JavaScript, ECMAScript 6, with all the nice features. And we will be using D3, data-driven documents. I guess many of you might have heard of this very popular library. So, some of you, obviously computer science master students or undergrads, this course is clearly, you can clearly do well in this course. But if you're a non-traditional student in this class, you should have some programming experience. So you should at least know, what is a function, what is a loop, what is an if statement, and so on. So if you know C, C++, Java, Python, or something like that, you'll probably be fine. If you know JavaScript, you'll probably have a much easier time. You also need a willingness to think about user-centered design. This is not your average CS course, right? So it's going to be hard for us to simulate real users, but we'll be trying. So we care about the human in the loop. You will have to have a willingness to learn new software and tools. While we'll be teaching you technology, it's going to be time intensive to simply get everything to work. So just be aware that this might happen. And you will need to build skills by yourself. So you'll be trying things out and how do I pass events between those different views and so on. We won't be explicitly teaching that. You should be properly equipped based on your prior experience to do these kind of things. Okay, here are a couple of formalities. I mentioned this already with the 6 homework assignment. The final project is 40%. And then the exams, we'll have 2 exams every Thursday before the fall break and the Thursday before the finals week. So that will be in lecture time. It will be in person here, on paper, and they will cover essentially what we covered in that period. So the midterm essentially will cover everything up to that point, and the final exam will not cover the whole course, but only the second part. In both cases, you will be asked to critique a visualization and to redesign a visualization. So there's a creative part to it too. So bring your pencils and anything that you need to draw. Obviously, we don't want you to cheat. We want you to do your own work. Please do make sure that there is no ambiguity. You are absolutely welcome to help each other, to discuss ideas, to discuss problems, to show somebody, this is my code, this isn't working, can you help me out? That is totally fine, but you cannot have the same piece of code submitted, ever. And we'll be automatically checking for plagiarism in all of your submissions. So you must write your own code, and if, for the homeworks, you should never use any other resources, you cannot copy code from anywhere online. For the projects, we're a little bit more lenient because we want you to build something in a realistic environment. I already discussed this a bit on Slack. I would like you guys to not use your devices when you're in here. The reason for that is twofold. A, there's research that shows that, for example, if you want to take notes and you do that by hand, that you retain a lot more. So you actually learn more if you take notes by hands, and the reason for that is that all of you are probably great typers and you don't really have to go through an abstraction process when you type, whereas you have to go through an abstraction process when you handwrite because you're just not as fast at doing that. And the other thing is, of course, I'm aware that I'm not as funny as whatever you're seeing on Facebook right now. And so it's hard for me to compete with some dancing kittens or whatever, and especially notifications from your friends and so on. All of these interfaces are designed to grab your attention, and there's a little red thing flashing in the upper right corner of your computer. You will simply look at it even if you don't want to. And so I would like you guys to pay attention. You don't have to come, it's not mandatory attendance. I would love you to come, but if you're here, please don't use your computer. I'm not going to be strict about this. So I'm not going to go to anybody and look on your screen and say, hey, put this away. This is more like a strong recommendation than an absolute rule. And we will have the coding lectures where you're actually encouraged to follow along, to play with this. All of this is going to be interactive, so obviously there you will need your computers. I hope most of you have already completed homework 0, which includes all the course survey. And then today we have the lecture on perception. And you should also be reading chapters 1, 2, 3 in the D3 book, and chapter 1 in the visualization design and analysis book. We will be pushing homework 1 out very soon, which is due next Friday. And then we will be doing on Tuesday, we'll be doing an introduction into Git and version control, because you will be needing that for your project, into HTML and into CSS. And we won't be focusing on all of the different HTML elements, but we'll be looking at some things like selectors and so on. And we'll be starting office hours. Okay, and the homeworks are going to be published in this GitHub repository. So what you can do is you can simply have a local copy of that repository. There is also some description somewhere on the website on how you can essentially fork that into your own repository and get updates. But essentially you can just download the homeworks from there. We usually give you a stub of code in addition to introductions that you can use to get started. And then we'll also push updates. Sometimes we make mistakes. And if there's anything wrong, we'll simply push an update to GitHub and we'll post on Slack when there is something like that happening. I also wanted, some of you might have already heard that, but I kind of wanted to emphasize it because A, I'm involved in this track, B, and this is a class that is part of that. There is a new track which is called Human-Centered Computing. You actually probably won't even find it on the website yet, but it's going to be possible to take this track starting in the fall. And this track has 4 required courses. One of them is this course. The other one is Human-Computer Interaction, which is taught by Mariah Maya. And then there is a statistics course, which is taught by Educational Psychology Department. It's Introduction to Stats and Research Design. And so what's nice about this course is that you get to pick a very balanced curriculum, both teaching you computer science skills. So you have to take at least 3 CS electives. But you can also take stuff like ethnographic design or digital fabrication or advanced human cognition or neuropsychology from other departments. So essentially to give you an opportunity to look beyond what is core CS and still get a computing degree. So that's the idea. And so if you want to know more about this, please feel free to talk to me. And then I was also asked to introduce a data science club. So we are starting a data science, many different data science initiatives. And one of them is this data science club, which is a club for students to participate. There's going to be events. Most of these events will have pizza. Particularly, we'll have a kickoff event where we have 6 data scientists from industry come and give essentially have a panel be there to answer your questions. I'm not totally sure yet what exactly the program is, but you can find out more about this at this URL. It's going to be in Warner Engineering Building, and there will be food. So this is the kickoff event. I would recommend if you're interested in this at all, just go there and learn what the Data Science Club is about. Okay, so this is my introduction, the formalities. Does anybody have any questions related to the structure of the course? If not, then we can talk about perception. Okay. So what I mean by perception? Well, there's 2 different things. There's perception and cognition. Perception is the identification and interpretation of sensory. The physical stimulus, like the electromagnetic wave hitting your retina to recognizing the information. And the perception is not neutral, it's not absolute. It is very much shaped by your learning, by your memory, by your expectations. And I'll have plenty of examples for what I mean by that in the rest of this lecture. Cognition, in contrast, is this higher level process, how we process information and apply knowledge. So we learn something. So a good distinction between those two is if you hear somebody speak in a language that you don't know, for example, you perceive them to speak, but you don't know the language, hence you cannot understand what they're saying. So this is a perceptive process, not a cognitive process. But if you understand the language and the words, then the cognitive process is engaged. So like these are just like a couple of keywords that are related to those two topics. In perception we talk about the eye, the optical nerve, the visual cortex, basic perceptions, early processing, things like edges and planes, and it's usually not considered to be conscious. And all of us have also built-in reflexes, like as you all know, and I'll show a couple of examples how we can leverage these lower level reflexes essentially for visualization too. And cognition is about recognizing objects, making sense of relationships between objects, drawing conclusions, solving problems, learning, and so on. So this is a good example of perception versus cognition, right? So here we have a list of words that are where there are colors written out, but they are rendered in other colors than they are written. So essentially looking at the colors is a perceptive process. Reading this and understanding, yellow, the color, the text is written in blue, that's a cognitive process. So there is this difference between what is there objectively in our environment and what do we see and perceive. So for example, who can see something meaningful in this picture? Just 3 or 4 people? 5, 6? Okay, so most people are getting it. This is like you can see a Dalmatian here, a dog. So like, here is the head of the dog, and here's the body, these are the legs. And so this is like something really tricky that we can do because we recognize that object, right? If we didn't recognize that object, we would be having a really hard time of seeing something here. And this is also a hard problem for computer vision, obviously. These are called emergence images, and this like once you have seen it, then you cannot really unsee it, and this is called perceptual hysteresis. And so there is research. Who can see something here? Elephant. Yeah, there's an elephant right here. And so here's the trunk of the elephant, the ears, the legs, and so this was actually a SIGGRAPH paper from recent, like from 2009, a SIGGRAPH Asia paper. And they did some studies on what is it that we perceive about those pictures. And so, like here it's quite obvious, the dog. They also published an algorithm that can generate those images. But what is interesting is that we cannot, like this doesn't work if we only look at patches of an image, like here. So we don't recognize those parts. Here this is like the trunk and these are the ears, but it's really hard to see for us. But if we do like a good rendering, this patch is very easily recognizable. So what this essentially tells us is that we need to like know the object and kind of like make sense of it as a whole. And they also did studies, like here particularly, this is like, there's somewhere the Stanford bunny in here. Now there's like a figure in here. So this is like the same picture before and after I hover over it, but one time it flipped on its head. And only very few people actually identify a person in this picture when it's flipped on its head. So if there's a weird pose, we don't actually recognize these objects like that. And if we flip that around, exactly the same image, a lot of people, like 90% or so, identify it. Okay, again, an example of perception versus what is really there. So we see it here, like we have like a 3D effect of this image, but in reality, of course, this only works because of the perspective. So we rely on our prior understanding of the world to interpret images. Here are a couple of other fun examples that simply illustrate that point. And we also tend to recognize things that we are very familiar with in things where they don't exist. So here, example, like not meant to be faces, but where we perceive them to be faces. And that's probably also the reason why sometimes you can see like a Jesus image in toast. So why am I showing you this? Like the take-home point here is that vision is constructed top down from the input. So what you see, when you see a thing, depends on what the thing is. What you see the thing as depends on what you know about what you're seeing. So our perception is not independent of our understanding of the world. We have these priors, we have these assumptions that we rely on to make inferences, and you'll see many other examples in this lecture. So let's talk a little bit about the fundamentals, like the eye, and I'm not going to make this into a biology lecture. I'm going to focus on the things that are relevant to visualization and related topics. So you've seen this in biology textbooks. What I really care about is our understanding for there is a difference between like this our central vision and peripheral vision. So we have the retina here at the back where light is projected onto through the lens, and in the retina we have a central like the fovea or fovea, which is kind of like the point of our sharpest vision. And this is going to be important. I'll talk about this later. And then we have, at one point in our retina, there's the optical nerve exiting, so we have these blind spots. There's a lot of examples on the internet that can illustrate how you can miss a point, for example, based on your blind spots. So how does this work generally? Like we have about 5 to 6 million cones. There's two different kinds of photoreceptors. These are cones and rods. They're easy to remember because cones, CO, can see color. So like the two first letters are the same. So we have 5 to 6 million cones which are responsible for the color vision, and they're really densest in the center of the eye around the fovea. So there's about 27 times the density in the fovea compared to other parts of the retina. And the fovea is responsible for sharp central vision. So here is this figure. Essentially shows us the relative frequency of these perceptors, and you can see it right here in the middle of the, like at the point where the fovea is, we have like the highest density of photoreceptors. And then we have about 120 million rods which are responsible for black and white vision. So here is like a good image, like a good illustration. A pretty old one actually. As you can see here, the rods that are sensitive to black and white, the cones that are sensitive to color vision. How does it look like under an electron microscope? So you can see the cones are much smaller and the rods are much bigger here. And we don't have, like we have a couple of different cones, and not all of, like they are sensitive to different frequencies of light, and we have more red, like the most red ones, fewer green ones, and the fewest blue ones. So we're kind of weak at discovering blue shades, which is probably like the evolutionary reason is there's not a lot of blue in our environment, right? If you go into like a natural environment, like into a forest, you won't be seeing a lot of blue there. Here this picture is quite kind of interesting. You essentially see that in the fovea we have these very densely packed cones, and in the periphery we have a mix between rods and cones. You can also see that like the distribution of our color sensitivity isn't equally spaced. One other thing that you might not be aware of is that we actually have only a very, very narrow field of sharp vision. So it kind of like we don't perceive it like this, but you can think of the whole visual perception process of more of like an ongoing construction project, because we can simply, everything appears sharp to us because we can move our gaze around and then essentially construct that image. But if we just fixate it on one point, this is more like what we would perceive if we looked at a spreadsheet. So we see like a couple of numbers really in focus here, and then a couple of numbers in the surrounding environment. We can see them well, but up here, what the details are is not obvious unless we move our eyes. And so how that works is we have these rapid, like interchanging operations between fixations and saccades. So we fixate on a point, perceive it, and then move our eyeballs around. And this, like the moving of the eyeballs, is called the saccades. The fixations last about 200 to 600 milliseconds, and the saccades, the moving between the different locations, is about between 20 and 100 milliseconds. cameras try to capture everything at the same quality, but our vision is very much like we have a central good vision, but we don't see our like wider surroundings that well. And this here is an example of an eye tracking study. So we can essentially, like by putting people in front of machines to track the movement of the retina, and by shining infrared light into their eyes and then using some computer vision, we can actually, and carefully calibrating this, like here is an example of such a setup. And there's now a better, like this one is actually like a state-of-the-art one. This is a setup that you would use in a psychology experiment where it's really about high accuracy, whereas this here is an eye tracking setup that you would use in a usability study, for example. If you want to see where do people look at your website or which parts of your visualization interface do people pay attention to. And so what happens is like what we can then essentially reconstruct the gaze path of people. And so I've prepared a video for that, which doesn't like to play. And again, the sound is a problem. Here is no sound, but this is like an aggregated study of what people look at when they see a commercial like this. So this is like a heat map, and I'll be replaying it. So what you always see is that people tend to focus on human faces, and then on like text, reading labels, and so on. So this is aggregated from multiple people, and now here I have one example of a guy singing karaoke while being eye tracked. And you can see he's basically erratic right now, no specific. And you see very well that this is not like a continuous scan along the text or every letter, but essentially like one word for one word, or how like 2 words and so on at a sequence. And this is like a demo video by one of those vendors. You can actually make those things with like pretty accurate precision, like for pretty cheap nowadays. But a professional system costs like $20,000. Okay. So here we have like infrared camera, then we have like a stimulus that could be a visualization that you're testing, and then there is like the software essentially tracks where you're looking at, and then either by fixating your head or by doing computer vision and head tracking, it can infer where you're actually looking at the screen. I also wanted to like emphasize this before, but we don't really have general purpose vision. We always frame things in the context of what we perceive. And so there's this famous example, the Ames room. So this looks like a perfectly normal room, and then we have a person going into that room. And this is not somehow digitally altered. This is just relying on our assumptions of what a room looks like.
Is it a different person?
No, it's the same person. You'll see why. So it's not a rectangular shaped room. It's like a, here's a slide for it. It's a room where you essentially break with the conventions that we assume, and then by carefully controlling where you what your perspective is, so you can't move your head around because of a video, or if you have just like a tiny hole to look through, you can actually create this illusion. We perceive this room as rectangular, and so if we don't have other cues like motion, parallax, and so on, we simply have no way of resolving these ambiguities. Is that clear? Okay, great. So we will be talking a lot about color, because color is one of the most important things in visualization and also the easiest. And in the future lectures, we'll be talking about how do we properly use color to encode data. So what is color? It's a visible part of the electromagnetic spectrum. It's between 390 and 750 nanometers wavelength. And there are special colors, which are the spectral colors, which are evoked by a single wavelength. Most colors that we actually see are unsaturated colors. They're a mix of multiple wavelengths of multiple intensities. And then we also have, just like the stimulus without color, the grayscale. So here you can see like the whole, or like a part of the electromagnetic spectrum, and you can see the the visible spectrum for humans is this kind of like smallish band right here. Color is not the same as wavelength. It's rather a combination of wavelength and energy. So here are two different examples that have both the peak at the same wavelength, but for example, we perceive a signal like this, where the relative energy intensity is concentrated around this wavelength as yellow, whereas we perceive like essentially a mix of wavelength with a peak around yellow as brownish. So this is how color is constructed. And it turns out that color is irrelevant to much of normal vision. So you can be colorblind and not be significantly handicapped in our world. So it does not help you perceive the layout of object. It doesn't tell us anything about how things are moving, nothing about the shape, and those are kind of like the evolutionary important pieces. What color does, though, is it breaks camouflage, and so the theory is that color vision was developed, for example, to identify predators in like an environment so that they stand out, and also to judge material properties like the quality of the food, so that we can easily perceive whether an apple is rotten, for example. Color has a couple of dimensions, and these are like not quite so easy to tease apart, but the obvious thing is hue. So hue is what we kind of, like if you talk about color colloquially, we usually mean color hue. So red, green, blue, and so on, like these are the different color hues. Then saturation is the purity of a color. So here we have the same hue with different saturations. The value, also called luminance or brightness, is the lightness or the darkness of a color. So high saturation colors have medium values. So what you really need to remember here, there is a difference between hue and another component that essentially shows us like something like the strength of the color. And my audio setup isn't working, but this is an interesting Radiolab episode that you should take a look at if you're interested in that. This kind of discusses our color vision and also the color vision of other animals, like the dog, who has much worse color vision than we have. But other animals have much better color vision than we have. And so they do really a good job of discussing this. This is a great podcast, so I'd recommend that you listen to that. And so, what is the role of objects in our color perception? Well, we perceive the color of objects because of their reflective properties. So if we're outside, the sun emits like a broad spectrum of wavelength, which we perceive as white. But if something bounces off an object, the physical properties of this object determine which wavelength is being reflected. And that is what makes up colors. So this is what the difference is between how we perceive an orange and green apple and strawberries, because they have different reflective properties. So, quiz. What are the primary colors? Red, green, blue, red, yellow, blue, orange, green, violet, cyan, magenta, yellow. Who thinks 1? Who thinks 2? Who thinks 3? Who 4? We don't have any printers here. The answer is all of the above. So it depends. What does it depend on? Well, there's a couple of different ways of how we can create colors. We can mix paint by mixing physically opaque paints, like something that is not translucent. And then we have red, yellow, blue as our primary colors, or orange, green, and violet as our colors. So these are subtractive colors using these reflective properties of material as I just mentioned. If we have translucent colors, then this is like ink mixing, what happens in your color printers if you have an inkjet printer, for example. So this is a subtractive mix of transparent inks, and here cyan, magenta, and yellow are the primary colors. You can have secondary colors as red, green, blue, and then it also turns out that for ink mixing it's hard to make proper. And this is a subtractive color scale. And then, as in all our digital devices, we mix light. So we don't mix any like pigments, but instead we mix light. And so we have an additive mix of colored lights. And here the primary colors are red, green, and blue. Secondary colors are cyan, magenta, yellow. And this is an additive process. So by adding two over on top of each other, we get like a red, green, creates yellow, green, blue creates lighter blue, and then here we have like this violet, and then if we mix all of those three, we have white light.
That doesn't look like blue, it looks more like purple.
More like what?
Purple.
What's purple?
Purple.
Yes. So this is actually a good point, and you will see that we can actually, like if we create a device, we can actually choose our primary colors. I'll be talking about how we can locate those colors in the gamut in a second. Right here, like this is the chromaticity diagram. This is essentially like a convention for a diagram where we have the pure colors on the other side, like this here is better annotated. So this is essentially a representation. This is not actually, like you're not able to see the real colors here. Because we are using a light mixing based three color source based display, but conceptually what you have here on the outer edge are the true colors. Inside these diagrams are all the colors visible to the average human eye. And then if we have a device like a monitor, we can pick 3 points as our like 3 pixels in our screen, and we can place them anywhere we would like to on this gamut, of course technical feasibility permitting. And so then we can essentially only display the colors that are in this triangle by combining those. So we have, like for example, if we want to show something very red, we only use this pixel, but don't use any of those pixels. So we can mix them. But we cannot, by using these 3 pixels here, we cannot display colors outside of here. So this is like an approximation what you're seeing here. It's not actually the color. So here is an example of like this chromaticity diagram with a specific gamut. And here are a couple of other gamuts from various devices. So you can have things like CMYK here, hexachrome, there's sRGB, and then there's an Adobe RGB version, which is a little bit bigger. So these are these different computer color models that you'll be using in a computer. So we won't be going much deeper into these because for visualization it is kind of important, but it gets tricky really fast, and you can actually, with a couple of simple guidelines, you can use that pretty well. So what is a color map? What do I mean by when I talk about color maps? How do I encode data with color? So we specify a mapping between color and values. So we have a couple of different color maps. You can have categorical color maps, ordered color maps, sequential, divergent color maps, segmented versus continuous color maps, univariate versus bivariate, and so on. So here is a binned discrete color map that maps to a continuous interval from 0 to 8. But we can't see every shade here. We only see like the integers basically here. This would be like a categorical color map. We can't really order between those colors. And I'll be coming back to this. Here's another sequential color map. This is a divergent color map. So here we have like a neutral point in the middle, and then higher values up here, and then lower values up here, down here. This would be a continuous version of that same color map. Or here is like a categorical color map again. So the problem is with colors is that we perceive millions and millions of colors, but it's really hard to tell them apart. So for example, this here shows you a picture, a graph of the internet in 2002. And the problem is that the author of this visualization has chosen to use 22 different colors to show different domains. But the problem is we can only perceive 7 or 8 or 9 different colors reliably. We can only distinguish these, like a very limited number of colors reliably. So here we have, for example, 5 shades of green. We can clearly distinguish them when they're close to each other, when they're really immediately in immediate proximity. But if you cannot tell me which of those greens here is this one versus which of those greens is this one. So this is not a good color map. So you should use only 6 or 7 or maybe 8 colors in practice. Of course you can use this for labeling, and this is a screenshot of a nice website. It's called Color Brewer, and you will be hearing more about that. We'll be using this a lot because this gives you good If you want to do quantitative data visualization with color is we shouldn't use value. We should use saturation, we should use saturation, we should use value, but we shouldn't use hue. Sorry. The problem with hue is here we have a continuously increasing field, and we can see if we use value, this is very obvious that this is a continuously increasing field. If you use something like a rainbow color map, where we try to emulate essentially the electromagnetic spectrum, what we get are these gradients that are actually not there in the data. So this helps us to kind of bin this data set, but it kind of introduces those wrong gradients. And very many of these rainbow color maps, they're not equally spaced. So you can see here that the green is much wider than the yellow. And this is kind of arbitrary. Why should it be like that? And so there's many downsides to that. So the rainbow color map is something that is very dangerous. So here's an example of the same data, of a flow data set with a rainbow color map and one with a value color map. And so you can see the extrema, the extreme values here quite well on the left, but then it introduces these wrong artifacts. Yet we see these kinds of charts a lot in scientific publications because they simply, it depends on your task. If you only want to see the highest value, this is actually quite good. But if you want to have a good understanding of the overall data set, then something like this is better. So here is just another example of rainbow maps versus a value color map. But people have actually studied this. And they have studied how well do we recognize or distinguish values if we, for example, have to do something carefully, like doing diagnosis by a radiologist. It's important that this person gets the colors right? And so there have been experiments where with the luminance color maps we can see that in these lower ranges here there is a big source of error. So this line here is high. But then, given starting here at this level, the error is very constant and pretty low. So the perceived values matches to the actual values, and so we can make faithful judgments here. Compared to the rainbow color map, there is quite a massive error here in the middle, and again at the end. So there is simply we lose precision if we use the wrong color map when we do data visualization. A common question is also, do I want to have a continuous or a bin color map? And it depends. So this is actually a study done by a PhD student in our group and supervised by Mariah Meyer, my colleague. And they have studied whether people are better at using binned color fields, like down here, where you have, this is an elevation map, and this is a binned color map, so we have 8 or 10 bins here, or a continuous color map. And so it turns out that people are faster with the continuous color map, but usually more precise on average with the bin color map. So this is kind of an ongoing debate, what is really the better approach here. And then when you use color, you should also be aware that a lot of people are actually colorblind. So 5% roughly of the whole population, 10% of males are colorblind, only 1% of females are colorblind. So if you feel comfortable, is anybody in here colorblind? Or has a weakness, a red-green weakness? Nobody? I'll test that. The theory again is that this is probably due to an X chromosomal recessive inheritance. Red-green weakness is very common. The reason is the lack of medium or long wavelength receptors or altered spectral sensitivity. So the green shift is the most common. And if we have a rainbow flag, this is what it looks like to somebody with normal color vision. If you don't have any green receptors, this is what this map looks like for you. Or if you have no red receptors, this is what this map looks like for you. So now I'm testing you. This is like one of those tests that you have to go through when you, for example, participate in a perceptual experiment. So what's the number here?
12.
Yes.
15.
So everybody who said that now is not red-green colorblind. Here?
7. 6. 23.
So
23. 23. It's 23.
it's a little bit ambiguous. It's either 73 or, yeah, I'd say 73.
26. 21.
Yes.
46.
45. have a certain color deficiency perceive our environment. And actually, I don't have a picture of that, but there's now glasses that can restore color vision by shifting the wavelength slightly. And so here's an example of, we'll be actually talk about this in more detail, but this is a figure by the New York Times that essentially shows government spending. Increased government spending is shown in green, and decreased government spending is shown in red. But for somebody who is red-green blind, this is simply not a good visualization because we can't tell that apart. Here's just another example. And if you ever create like a visualization or like even just a piece of artwork, and you want to see if that is actually easily recognizable by people with color deficiencies, you can go to one of these websites, upload your data or upload an image, and then they will show you how your visualization looks like for these various conditions. You can actually also do this if you use ggplot. In R, there's now a library which I just discovered like a couple of days ago, where you can plot your original charts for all of these different color deficiencies. So this is also quite handy. Okay, so next I'll be talking about how color brightness is relative. It's like we don't have an absolute perception of color. So there's the thing with simultaneous brightness and contrast. So the perceived brightness of an object is always relative to its background. So all of these blocks here have are the same shade of gray, but we perceive them to be different because they're against different backgrounds. So here's another example. This is called the Chevreul illusion. This is simply like a set of color saturations here, but what we perceive is not what actually is in the data, this stepwise function here, but we actually perceive these edges as enhanced. This is like just how our perception works, and that can be a problem, especially in computer graphics, because in computer graphics we of course don't have perfect shapes. We always have some kind of triangle mesh. And so what we want to do is we want to use shading that kind of avoids that. And if we had just flat shading, uniform shading, then we would get these like increased effects around the edges here. If we did Gouraud shading, which is better, we still get these effects because it's not continuous. And if we use Phong shading, which was actually developed here in Utah, then we have like this continuous perceived profile in addition as well. So these Chevreul illusions, they amplify artifacts in computer graphics shading. This is the chord suite illusion. Which of those two blocks here is darker? Like the ones in the middle.
See?
So I hear a lot of this. I hear the same, but it's of course the context here. Like if we put a color in here in between them, we can actually see that they're the same, but we don't perceive them as the same. Like even if we try, they don't look the same because we make assumptions about light, about shadows, how they fall. And so we assume like a light source here on top, and then we assume that since this goes back, that this has less light, and therefore we perceive this here to be lighter than the one up here. But in fact, they are the same color. They're just like, because we have this built-in perceptual model of the environment, they do look different to us, and it's really, really, like, I can know it, and it still looks the same. They're still, like, there's no way for me to say that these are the same colors. There's a lot of similar examples here. This is a psychologist lab website where you can, flash player. Where you can do these kinds of experiments. This is again a point that has a consistent color, but we perceive it to be lighter at the right and then darker on the left, just because of the background. But if you put here this thing behind it, we obviously see that it is the same color in all of these phases. Here's the Horn-Sweet effect, and there is similar color effect. So please go ahead and play with that. I have a couple of more examples in my slide. So the dress weave. What's the answer? Is this dress black? Everybody knows that it's in fact black and blue, but this is exactly this problem. It could be that this dress was photographed under a yellow light source or under a blue light source, and depending on that, its actual color is different. And so here is a good example of somebody clipping out this, moving it. So, yeah, just to illustrate that our perception of color is relative. Which of the axes is darker? Left or right? Right. Who thinks to right? They're the same problem. They're the same. Like now you know. You can look at the intersections here, and you can see there is no difference between them. Those are obviously different colors, right? They are actually different colors because we can see they're right next to each other. So this one is darker than the other one. But if we separate them, they suddenly look the same. So we can also make colors that are not the same look the same depending on context. So here's an example. This is from an actual, this is a figure taken from an actual paper. And in genetics, it's very common to use these heat maps, these red-blue heat maps, or black-green or red-green heat maps, where you shouldn't use red-green, you should use red-blue. But the point here is really that the two fields that are marked with a star here have the same underlying scalar value. But we perceive this one here as much higher than this one just because of its environment. And this sorting here is likely arbitrary. So we are being deceived in interpreting this data set accurately by the surroundings of these values. Okay, so now I want to do a design critique. Okay, so here's a chart, and I have a printout for you. I'll be handing this out. And then, before I hand this out, this is a chart of causes of untimely death in the world. And so Bill Gates picked this as his graph of the year. I think it was in 2013. And he said, I love this graph because it shows that while the number of people dying from communicable diseases is still far too high, those numbers continue to come down. But there remains much to do to cut down the death in that yellow block even more dramatically. We have the solutions, but we need to keep up the support we're trying where they're being deployed. And so now I would like you guys to take a look at these charts. I'll hand them out. There's a couple of questions in here. Team up with your neighbors and discuss the questions on here. The questions are things like, what questions does this visualization answers, what design principle best describe why it is good or bad. This is something that we haven't really talked about, but you can speculate, and then give up personal preferences. Why do you like or dislike the visualization? And then we will be discussing this visualization as a group, and then when we're done with that, you'll have 5 minutes to create redesigns. And I have paper if you want to sketch. And then afterwards I'll be showing you a professional redesign of this chart. Okay, would you mind helping me hand this out? Thank you.
This is nothing like on the rest of the chart. Also, you don't get a sense of volume.
You guys can be shared.
It's not.
You
It doesn't really go with the cube.
Here, that's another one. Everybody have like at least one. What does it show? What doesn't it show? What could you do better? And so on.
So the first thing is what question is
It's like all these different those
under different layers, they have like entries and then they have what are the different kinds of and the same goes for oh, okay. What is that? Oh, okay. Got
They are just the gradients and colors.
And then there's a blue ball. That's positive. And those are types of cancer. There are cancer, blood cancer. But I didn't get this thing under non-communicative diseases. So these are not diseases. Over here, more like different parts of the body. Here, it doesn't say anything about this. Here, these are different parts of the body. Yeah, but this is like stroke. Stroke is not a disease, but it's not a disease, it's more of life. It's not what are the different yeah. problems. These are not even deaths. Because here you have birth problems. Like TB, starvation, people don't really die because of this. These are just problems. And these are injuries and these
Okay, so let's discuss this as a group. So, what is the data that is shown in this chart?
Can you repeat the question?
What's the data that we see in this chart? Please raise your hands and I'll let one of the other. Yep.
So it's a change, percentage change annually in the number of deaths in each segment of each disease.
Yes, that's a part of the data set. That's correct. Anything else?
The proportion of deaths caused by the three categories. Injuries and non-communicable diseases.
Exactly. So we see the proportions of the three big categories. Anything else?
It also gives a relative number of, instead of like each block is showing the number and the percentage, like how is it going up or down, and what was the actual count or the proportion of the counts. So both.
Yeah, I agree with the proportion of the counts. The actual counts are
Not there, but you can probably like take a rough guess.
Yes. Anything else that's in the data here?
The three different bars at the bottom, it tells you the increase or decrease in the past 5 years.
Yeah, this is a color legend, right? So it tells us like 43 color, for these three big blocks. This is the color legend here. Anything else? There's one special call out here.
For cancer.
Yes. So cancer is an additional category here because it's a significant chunk, but then we distinguish between the subtypes of cancer. So cancer is called out. Okay, so how is the data encoded? So let's say, let's start with how are these relative frequencies of death, how are they encoded? No, like not the change, but the actual, like the frequencies.
Area.
Well, basically it's kind of telling you that there's been more people dying out of stroke than, let's say, lung cancer, because stroke takes a bigger part of the...
Yes, I would say that the stroke is smaller than the cancers, but...
Oh, I mean lung cancer specifically, yes.
Yes, lung cancer specifically, that's correct. So I heard here the size of the area, that's like what I was looking for. The size of the area tells us what the relative frequency of these causes of death is. What is color encode?
The category.
The category and the change. So both are correct. Is this a good color map?
No.
Why not?
So there are certain shades.
Please rate like.
There are certain shades which are like pretty similar. I mean, difficult to distinguish. Like, what's the frequency difference?
Yeah. How can you tell -1% from 1%? It's really hard to tell in this chart, right? So what could they've done instead?
Put the percentage. Put specific percentages on the...
That would be a possibility, labeling.
Value changes?
Yeah, exactly, but I'm trying to get first to something else. Yep.
They could make the larger the percentage, the bigger space it takes up on the graph.
Yeah, but like I'm assuming that we're taking like keeping the space. I just wanted to like because the space encodes something different, right? And we kind of given that space, we want to use a better color map.
We have two of those, before and after.
Yeah, so we could have two of those, like small multiples.
Or you could use two very different colors instead of just black and white. You could use red and green, which are extremely different.
Yeah, so you could use a diverging color map with a neutral middle point, right? So you could, instead of using these colors to identify the categories, these categories you could frame them, and then you could use like red, white, blue, like red being a decrease, white being neutral, blue being an increase. So that would be, by not changing this figure too much, that would be a solution to just improve that color map. So anybody want to tell me about whether they like this chart or dislike this chart, and why?
It's a good chart, but I can do it in a different manner by stacking the percentage changes like in a zero fashion, and 0 being the center, and if it's increased, stack it on the right side and decrease, put it on the left side.
So there are other ways to display this data. Anybody want to share their opinion? Yeah.
So it does not give a clear idea about the proportion also, because some shapes are somewhat equal.
Yeah, exactly. And so it's also one other weakness here is what is that? There's simply no space for the label, right? So it's not like you can make an argument this is small and therefore not important, therefore I don't need to label it, but there could be a situation where you care about that.
I don't like the three-dimensional. Like, why did they make it three-dimensional? The only thing that they put on the third dimension is like the title of the overall.
Yes.
Group.
So there is a 3D effect. There is a It looks fancy. And we will learn that just from a purely perceptual, theoretical point of view, 3D is very often not a good choice. It's really hard to make comparisons in three-dimensional space. I have many more examples for you in the rest of this lecture. But on the other hand, there's an argument to be made. This looks cool. If you flip through a magazine while you're waiting for in your doctor's office, you might actually pay attention to it, right? And what I'm kind of trying to tell you with this is that there is always different motivations of why you want to create a chart and different contexts, different tasks, different people. And there's not one solution that is perfect for everybody. You don't want to have a chart like this in a government report where somebody needs to make a decision based on that, because it's not accurate, it's not reliable, it doesn't present information reliably. But if you just want to tell people, hey, infectious diseases are a big problem, and it's been getting better, then this chart is maybe not the worst ever. Like the color map is terrible, but just making it look nice is not always a sin. And so we'll be talking about what's called chart chunk. What we can add like as extraneous elements to make your things look pretty. What is the benefit of that? What are the downsides? There's different schools, there's different opinions, and this is what makes this visualization also subjective, right? We can argue about those things, and there are really hot arguments in the community about what is the right approach. Nobody would really argue for that 3D this way is a good approach, but at least it makes people pay attention. Okay, so now I want you, everyone, or as a group, I want you to create 3 different designs, sketching them, of encoding the same data, just with your own design. And maybe think of something that is less flashy and more pragmatic. And try to encode all of the data sets. You don't have to finish it up, just like sketch it so that you have an idea. Make sure to encode all of the important data points, and then later I'll show you one solution. And I'll be coming through and snapping pictures of your design, and maybe if we have time I'll show them on the screen and you can talk about them. And if anybody needs paper, I brought paper.
So what kind of chart? Is it going to be a rectangular chart?
So go ahead. Sure. So this is a very common way of showing complex
Then in this case, how would you point out the but then these gradient correspond to the higher the number, more serious than what is the area
Okay, so turns out it's too late for us to discuss this. So what we'll do is please bring your sketches to the next lecture. We'll either discuss it on Tuesday after the HTML SVG introduction, but it's important that I do the HTML SVG introduction first because you need this for the homework. And then on Thursday, we will, if we don't get to it on Tuesday, we'll discuss it on Thursday and then continue with the perception lecture and then follow up with data and data types on Thursday. So I hope you had a good first week of classes and I'll see you guys on Tuesday.